I'm Dr. Nupia, working as Assistant Professor in Department of Applied Science and Humanities, associated with ABES Engineering College, Ghaziabad. In this session, we will discuss about chromophore and auxochrome with example and numerical problems. And the topic we are going to cover: brief introduction of UV visible spectroscopy, chromophore and auxochrome, Woodward-Fisher rule, and the calculation of lambda max by Woodward-Fisher rule. We know that spectroscopy is a technique which is used for the characterization of organic molecules. And UV visible spectroscopy is based on the when a UV radiation interact with a molecules, the valence electron get excited from ground state to the excited state after the absorption of UV radiations. And UV visible spectroscopy gives the information how much energy is absorbed by the molecules in the form of spectrum, and which is known as lambda max. Lambda max is also responsible for the color of the molecules. Here we can see that the red color of the tomato is due to the presence of lycopene. This is a conjugated diene and absorb the UV radiations in UV visible region and give the spectrum in the range of 400 nanometer to 5,500 nanometer. Similar, the orange color of carrot is due to the presence of beta carotene. Now, chromophore and auxochrome are basic terms which is used in UV visible spectroscopy. We know that organic molecules absorb the UV radiation. So, the part of molecules which responsible for the absorption of UV radiation is known as chromophore. It is a Greek word. Chromo means color, phore means carrier. That means the chromophore are also responsible for the color of the molecules. They absorb the UV radiation in the region of 200 to 800 nanometer and undergoes pi to pi star transition and shows some strong absorption by additional non-bonding to pi star transition. For example, nitro, carbonyl, and diene system is known as chromophore. There are some simple chromophoric group. For example, carbonyl, azo group, nitro group, conjugated diene, and benzene are a simple example of chromophoric group, and they absorb the UV radiation and give the absorption maxima in the range of 200 nanometer to 350 nanometer. Chromophore also two types, independent and dependent chromophore. If only one chromophore is sufficient to impart the color of compound is known as independent. For example, azo group and nitro group, which only responsible for the color of compound. Generally, the nitro compound have the yellow color. Secondly, dependent chromophore. If more than one chromophore is required to impart the color of compound is known as dependent chromophore. For example, if we take only one ketonic group, the molecules are colorless, but diacetyl group which have two ketone group is a yellow color. So the ketonic group is a dependent chromophore. Now, auxochrome are a saturated unsaturated group with non-bonding electron attached to a chromophore, which modify the ability of chromophore to absorb the light. That means auxochrome individually does not absorb any UV visible radiation, but when we attach with chromophore, chromophore show the bathochromic shift. Many of the time, auxochrome have non-bonding electrons. For example, hydroxy group, epoxy group, amino group, they have non-bonding electron as a lone pair. Auxochrome also two types, basic, for example, amino group, and acidic auxochrome, for example, carboxylic group, sulfate group, etc. Now we will discuss about what is the effect of auxochrome. Here we can see that benzene is a simple chromophore and so the absorption maxima at 21600 nanometer with lower molar absorptivity coefficient and undergoes to pi star transition. But when we attach hydroxyl group, lambda max of increase at 200 nanometer with high molar absorptivity coefficient and undergoes pi to pi star transition with additional non-bonding to pi star transition. Here, if the lambda max is 280 nanometer with high molar absorptivity coefficient and undergoes pi to pi star transition with additional non-bonding to pi star transition. So conclusion is that chromophore is a part of the molecules which is responsible for the absorption of UV radiation and auxochrome are responsible for the bathochromic shift, that means red shift of the chromophore. Now we will discuss about Woodward-Fisher rule. Woodward-Fisher rule basically used for the theoretical calculation of absorption maxima of molecules. In 1945, Woodward gives certain rule for calculating the wavelength maxima absorption with molecular structure. In 1959, Fisher modified these rules with experimental data, and the modified rule is known as Woodward-Fisher rule. This rule only applicable for conjugated diene and triene for the aromatic compound and alpha, beta, and saturated carbonyl compound. First, we will discuss for the conjugated diene. Conjugated diene are organic compound containing two or more double bonds, each separated from one another by a single bond. There are some steps for the calculation of lambda max by using the Woodward-Fisher rule. First, we have to identify the diene species. That means we know that every system which have diene absorb a fixed amount of lambda max, which are known as parent value or base value. We have to find out what is the system of diene. After that, we have to calculate the number of ring residue or alkyl group, number of the exocyclic double bond, and number of the additional conjugated double bond. So the overall lambda max absorption maximum of molecules is equals to the base value plus subsequent contribution plus other contribution. Before moving to the calculation, we have to understand the type of conjugated diene. If two double bonds are present in a linear form, is known as acyclic diene. If two double bonds are present in a same ring, is known as homoannular diene. If are present in different ring, known as heteroannular diene. If double bond are present in the ring, is known as endocyclic double bond. If double bond are present outside the ring, is known as exocyclic double bond. If there are more than two double bond, is known as double bond extended conjugations. Here some base value for conjugated diene. For homoannular conjugated diene, the base value is 253 nanometer. For heteroannular conjugated diene, 240 nanometer. For butadiene system and acyclic conjugated diene, 270 nanometer. For acyclic triene, base value is 245 nanometer. There are some increment if alkyl substituent or ring residue are present at the conjugated system. We have to add on the 5 nanometer. If exocyclic double bond are present, we have to add on 5 nanometer. If double bond extended conjugation are present, we have to add on 30 nanometer. If at the conjugated diene some auxochrome are present, like if chloro and bromo present, we have to add on 5 nanometer. If alkoxy group are present, we have to add on 6 nanometer. If sulfide group are present, we have to add on 30 nanometer. If amino group are present, we have to add on 60 nanometer. Let's discuss with examples. Here we can see that in this molecule, two double bonds are present in two different rings. So this is a heteroannular conjugated diene. The base value of heteroannular conjugated diene is 240 nanometer. And we can see that here 3 ring residue also present. We have to add on 3 multiply 5, 15 nanometer. and one exocyclic double bond. So we have to add on 5 nanometer. So the overall lambda max of molecules is 234 nanometer. In second example, both double bonds are present on one ring. So this is homoannular conjugated diene. So base value is 253 nanometer. Here also 3 ring residue also present. So we have to add on 3 multiply 5, 15 nanometer and one exocyclic double bond. So we have to add on 5 nanometer. Overall lambda max is 275 nanometer. Now we will discuss about aromatic compounds. So if aromatic compound is ketone, the base value is 246. If aldehyde, base value is 250 nanometer. If acid, base value is 230 nanometer. There is increment if alkyl and ring residue are present at ortho and meta position. We have to add on 3 nanometer to this value. If it is present on para position, we have to add on 10 nanometer. For auxochrome, like if chloroauxochrome are present at ortho and meta position, there is no increment on base value. If chloro group is present at para position, we have to add on 10 nanometer. If chromo is present at ortho and meta position, we have to add on 2 nanometer. If it is present on para position, we have to add on 15 nanometer. If hydroxy and methoxy group are present at ortho and meta position, we have to add on 7 nanometer. If it is present at para position, we have to add on 25 nanometer. If amino groups are present ortho and meta position, we have to add on 30 nanometer. If it is present at para position, we have to add on 58 nanometer. If substituted amino group present at ortho and meta position, we have to add on 20 nanometer. If it is present at para position, we have to add on 85 nanometer. Let's explain some example here. In first example, we can see that this is a ketonic group. So the base value of aromatic ketone is 246 nanometer and two hydroxy group are present, one at meta position and one at para position. So the increment for OH value at para position is 25 nanometer, at meta position 7 nanometer. So overall lambda max is 278 nanometer. Here we can see that a carboxylic group, so the base value for aromatic carboxylic acid is 230 nanometer. Here three hydroxy group are present, two at meta position and one at para position. So the increment for para position is 25 nanometer and increment for meta position 2 multiply 7 nanometer is equal to 14 nanometer. So overall lambda max for these molecules is 269 nanometer. Now we will discuss about alpha beta unsaturated ketones. If alpha beta unsaturated acyclic ketone or 6-member ring ketone, so base value is 215 nanometer. If alpha beta unsaturated 5-member ring ketone is 200. If alpha beta unsaturated is aldehyde, base value is 207 nanometer. For alpha beta unsaturated acid and ester, base value is 195 nanometer. For the increment, if alkyl substituent or ring residue is present at alpha position, we have to add on 10 nanometer to base value. If it is present at beta position, we have to add on 12 nanometer. If it is present at gamma and delta position, we have to add in 18 nanometer. For the auxochrome, for example, chloro is present at alpha position, we have to add on 15 nanometer. If it is present at beta position, we have to add on 12 nanometer. If bromo are present at alpha position, we have to add on 25 nanometer. If it is present at beta position, we have to add on 30 nanometer. If hydroxy and methoxy group are present at alpha position, we have to add on 35 nanometer. So beta position 30 nanometer. If amino group are present at beta position, we have to add on 85 nanometer. Let's see some example. Here we can see that this is a alpha beta unsaturated acyclic ketone. So the base value is 250 nanometer. Here two alkyl group are present at beta position. So the increment is 2 multiplied 12 is 24 nanometer. The overall lambda max for this molecule is 239 nanometer. In this example here we can see that this is a alpha beta unsaturated 6-member ring ketone. So the base value is 240 nanometer. Here we can see that this is alpha, beta, gamma and delta. So the here two ring residue at beta and delta position. For the beta ring residue, the increment is 14, 12 nanometer. For delta ring residue, the increment is 18 nanometer. Here one double bond is extended double bond. So we have to add on 30 nanometer and one double bond is exocyclic double bond. So we have to add on 5 nanometer. So the overall lambda max for this molecule is 279 nanometer. So this is overall from Woodward Fisher rule from my side. Hopefully this video is beneficial for you. These are the references.